Ladies and gentlemen, sorry, it's 7:02, so I'm just going live so that people on the YouTube channel can see what's going on.
Okay.
Just to let you know, we are live on the internet, so the microphone is picking up any chatter in the room, so just make sure that it's kosher.
I think we'll maybe give maybe one more minute for people to come in, or do you need to get yourself a refreshment? Feel free to do so. Of course, there are some puzzles on your table already, if you want to get cracking into those. And we are going to be doing lots of these puzzles today as well. Okay. Did you all bring a pencil? You come to a math presentation without a pencil? Let's see what we've got. See you later.
If you need a pencil, Laura Sternad, one of our facilitators, has a bucket of them.
God bless Laura.
And the teacher librarian that stocks that. And has them sharpened. Right? These are the small things that we're really grateful for.
Thank you, Monica Dion. The teacher librarian that keeps all this stuff stocked.
Oh, now you broke it. That's my lucky pen. Have you got one? Okay.
This isn't go long. Right, good evening everyone. Thank you so much for joining us. This is our third of 4 math cafes and our focus is on spatial reasoning. My name's Mike Jacobs. I'm a math consultant with this school board and basically that means I've worked with teachers and parents and children, kindergarten all the way up to grade 12, just thinking about better ways that we can learn about math and do math. My name is Christine Corso. I am also a consultant with our board for numeracy. We also have Natalie Reed here, who is an elementary school math facilitator with 3 of our elementary schools. We have Laura Sternad as well. She is another math facilitator in 3 of our elementary schools. We have Tracy Burrell, who is our superintendent of teaching and learning, and she's here on behalf of Rosemary LeClaire. Rosemary's mother passed away last week, so we'll talk about that in our intentions. And we'd also like to thank, and I'm kind of playing on the other side of the post there, our DC PIC. Because of them, we are able to provide this evening, and we greatly appreciate it. We also acknowledge that Amanda Raffi, who is our communications officer, she certainly helps make sure that lots of this information gets onto the website and accessible for us. So we appreciate that.
And finally, we've got one of our technology consultants, Brian Chen, who's working his magic with the computers, so we're actually live streaming now. So yeah, everything we say is being broadcast. So you need to tell us something. Okay.
I try to tell my kids that I'm a YouTube star.
Yes. Yes.
It's not really, it's not really going.
Not quite viral.
No.
Not
no.
yet.
Yes.
Maybe maybe this will be our breakthrough.
Try tripping and falling, it might help.
Wait, really at the beginning of the presentation?
Sorry.
So my superintendent wants me to hurt myself. Is that what it is? Is that okay, right, okay. We will start, as always, with our Catholic School Board with prayer. We'll keep Rosemary in our prayer because she's lost her mother this past week. Does anybody have any other intentions that they'd like to share at this point? Well, burning intentions that we might be holding closer to our heart. Let's start by saying a Hail Mary in the name of the Father, and the Son, and the Holy Spirit. Amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of our death. In the Father, and the Son, and the Holy Spirit. And as always, we here in the Durham region respectfully acknowledge that we are on the traditional lands of the Mississaugas of Scoopville Island. So, as I said, this is the third of our Math Cafes. We've had a ton of fun getting ready for these and delivering these. Our next one is on May the 14th at Monsignor Paul McGuire School. This is about problem solving. But today, we are focusing on spatial reasoning, which is never used to be my favourite area in math. In fact, I would say it was probably one of my weakest areas in math. But since I've taken on this role as a consultant and I've gone into kindergarten classes and elementary classrooms and played with blocks and geoboards, my spatial reasoning has gotten better and has made me a better mathematician. And I now get probably too excited about spatial reasoning, so I'm going to have to try and dial it down a wee bit. But we've got a ton of stuff that we'd like to share with you that you can take home and use that to help with your sons and daughters. Just a quick show of hands gives an idea of the age range of your students. Kindergarten, do you have any sons and daughters in kindergarten? Fantastic. Grade 1, grade 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that doesn't help us narrow it down too much to a particular grade, but we'll manage anyway. All of these are focusing on different areas. It was kick-started by the Ministry's new document that focused on the fundamentals of math. And as we looked at in our first session, this really talks about 5 big areas to do with number sense, working with numbers, number properties, math facts, developing mental math skills, and proficiency with operations. I think one of the things that we're actually feeling about this is that one of the things that's probably missing from that is this idea about spatial reasoning. This is a lot of number sense, but it forgets about spatial reasoning. And I'm hoping that what you'll see today is as we work through this, you'll see that spatial reasoning is as important as number sense. And it actually helps improve number sense. In fact, we think they're kind of symbiotic, the spatial reasoning and number sense. They go hand in hand, and you can get better in one by getting better in the other. So our goals are, we are going to learn what spatial reasoning is. We're going to learn how we can improve it for our students, and also we're going to learn some things that we can do as parents to help our sons and daughters. Now, the first thing is that spatial reasoning encompasses lots of things. And I'm not going to go for each one of these, but I'll pick out my favourites. The first thing is all about composing shapes. So putting 2 shapes together, 2 triangles together to make a square or a rectangle or even a hexagon. But it's also about, not just composing, it's also about decomposing. And you'll see how composing and decomposing shapes helps us to understand how to compose and decompose numbers as well. The other thing you'll see is imagining how objects rotate or reflect in space. And finally, it also includes diagramming. And you'll see some of the activities we'll do today involve maybe working through a flow chart, anything that requires some abstract visualization, that involves spatial reasoning.
And this graphic actually is from one of our ministry documents. The ministry previously had included documents focusing on various aspects of math, and this is a publicly available document, and it's focusing on spatial reasoning. So this is where that comes from.
Now, all the material that we share with you today will be available on the DCPIC website afterwards, okay? Now, there's some fantastic research about the importance of spatial reasoning. There's a massive, massive study, tens of thousands of students, that looked at, measured the spatial reasoning abilities of very young students, kindergarten students, and also their number sense and also their language skills. And then it tracked them over a few years, and then it measured them again. And it said that of all the three things, spatial reasoning, number sense, and language, the biggest predictor of future success was spatial reasoning. It was a better predictor of language ability and number sense ability than the language and number sense itself, which is kind of astonishing, really. But it's a study that's been replicated. So it's one of the things that it's really important that any curriculum must have spatial reasoning involved. The other thing that I really liked is that spatial thinking is malleable. It can be improved through education. And I'm going to say again, I confess, I was pretty rubbish at spatial reasoning. And it's probably because it was the way it was taught to me. I didn't have any good hands-on activity. Okay? But now I've had a much better experience. I think my spatial reasoning has improved. Okay? So I know sometimes people will say, oh, I'm no good with those kind of puzzles. Say, just keep trying. It will click.
Or
Right?
people will also say, I'm directionally challenged, but it's our experience. And so if we hear ourselves thinking or saying those things, we have to be careful when we say that to our students or to our children, because they will take that quality on themselves, right? So the science proves that you can have better spatial reasoning with more practice or with different experiences. So we're really going to focus on some of those experiences this evening.
So, the first thing, we're going to do some math together, okay? Because that's why we came here. So on the handouts that are on the table, if you turn to the second page, you will see 4 different questions. And just for fits and giggles, I'm going to give you some time to do these questions. The top 2, the 2 you see there, are primary questions, and the 2 below are junior questions. Okay? So that's what they do at the end of grade 3 and what they do at the end of grade 6. And we're just going to give you 3 or 4 minutes to have a go at those. You are allowed to talk and share your answers. This is not an official EQAO test. Okay? We're not going to give you detention if you talk. All right? So 3 or 4 minutes, and then we'll put it back together.
that we use in classrooms. So geoboards, linking cubes. So they actually built it to answer the pencil and paper question. So Mr. Jacobs, you know, often you'll say this phrase, you'll say that you got math bumps.
I did get that. Yeah.
It's fantastic because one of the things that we want parents and kids to know is when they do the EQAO assessment, they are allowed to use these materials. So some of you grabbed some of the cubes and started building, and we're wondering if that's okay. So students are encouraged to use all the materials that are provided to them in regular instruction. They will be allowed to use things like geoboards. Okay, we will use different items today like the tissue paper. So all of those things, they don't have to have it all mentally. They can use those manipulatives to demonstrate and better answer the question. And I also saw the other math bumps that I kind of had is the gesturing that was happening. I saw lots of you, and it was so powerful because this is what teachers do when we're in school. We see kids going like this, or with their pencil like doing the faded line. They think it's the line of symmetry, but they don't want to commit to like a whole dark line. But that's demonstrating thinking. And that's what teachers are looking for when we are doing kind of activities like this. So it's great to see that we as adults do those as well.
Yeah.
So during the EQAO, do they put like sets of this out on the tables for the kids to like go to, or are they off on the side for them to read for?
So that's in their environment, whatever their classroom environment is, they are allowed to have those materials as they would be. So if the teacher has them off to the side and their kids have been routinely getting up and going and getting them, or if they are coming to the tables themselves when students need to write in an alternative environment, a kit goes with them. And there is a list available on the EQAO website that tells us what manipulatives are allowed. So it's meant to be like what is already done within the classroom environment, as opposed to making sure every single child or whatever has, because they have to be in an isolated spot. But yeah.
It's sometimes a tricky thing because everything they might need, you can't have on their desk because there'll be no room to actually work. And the other thing that teachers can't do is something I did 2 or 3 people as they're going around and some people are trying to figure out the cubes one in their head. I said, you know what, I would use these cubes. So, oh yeah, that helps. We're not allowed to do that in EQAO at all. We're not allowed to give any sort of prompts whatsoever. It kind of goes against the way you do something normally in the class, but those are the regulations.
I'm just curious because I see our son being very much like he's allowed to use his paper and his pencil. Like,
Yeah, so as a teacher, one of the things we want to do is say, this is what I do as an adult. If I'm using cubes and it helps me, guess what? It's going to help us. That's what mathematicians do. Mathematicians use these tools to help us become better thinkers and kind of take away the stigma of using these things. And I'll show you something later on about a famous mathematician who uses tracing paper and mirrors to learn about geometry.
And we have talked in our previous math cafes, if you've been here with us, or if not, something that's called going from a concrete. So those materials that you have, those blocks, those geoboards, that's a concrete experience, to a diagram, to something symbolic. So we're going to kind of discuss a little bit about that as well.
So, just as a heads up, the first question there was answered correctly by 70% of students provincially. Okay, which shape has only one right angle? Correct answer is. Yeah, I feel really nervous now. Did I get the right answer? The correct answer is, it's that one. Yeah, okay. We know some students put that one because they didn't read it carefully enough. And they just thought, oh, it's got right angles. Look at that. I know it's got right angles. It's got them. We also know that some people don't think that's a right angle because of the way it's pointing. And I'm not trying to be funny here, there are some people who think that's a left angle. And this is one of the things that we learn, is that we need to develop a more flexible understanding of what shapes mean, what angles mean, what triangles look like, what triangles can't look like, but what they can look like as well. This is meant to be a square. It's a square on your sheet, but there's some sort of weird distortion thing going on with the projector, so it looks like a rectangle. But which shape below is vertical, horizontal, and diagonal lines of symmetry? This one was answered correctly by 45% of students. Okay, this is a trickier question. This is an application question. This is a knowledge question. And it doesn't matter if it's grade 3, grade 6, or grade 9. Our students are doing really well on the knowledge type questions. Okay, the questions we're getting stuck on are the application and thinking questions. So how might we get people to understand this? Well, it is a rectangle. I know a lot of adults think that a rectangle has 4 lines of symmetry. 1, horizontal, cuts it in half. Yeah, do you all agree line of symmetry will cut it in half? Yeah? 2, vertical, cuts it in half. Do you all agree line of symmetry cuts it in half? Yeah? Diagonally. Does it cut it in half? You all agree that a line of symmetry cut it in half. You all agreed, and I've said it. And I've mistakenly said a line of symmetry cuts in half. So can you see how some kids and some adults might think, oh, that cuts it in half. It's got to be a line of symmetry. And I've even been with kids that said, well, look, fold it. And they fold it, and they say, see, line of symmetry. I said, no, it's not. I said, well, look, it cuts in half. I said, no, all right. The idea of symmetry there is that when it folds exactly onto itself. And it's usually then just a 10-second correction. The kids go, oh, what about this one then? And they go, oh, no, not a line of symmetry. I said, yes, it cuts it in half, but a line of symmetry has an awful much more. It has to perfectly fall onto itself. And that is how kids initially learn about symmetry. That's not how I learned about symmetry initially. I was given something like that and told, draw the dotted lines on, okay? And sometimes I did it by luck, sometimes I got it wrong, all right? So let's look at the next questions. What was the percentage for this? It says it in the notes.
Okay, so for question 6, 52% of our students answered that one correctly. And that's a thinking kind of question, meaning that they had to come up with some sort of plan. And they had to execute that plan in order to answer a multiple choice question. And so we saw lots of you coming up with a plan of, hey, yeah, let's build with the blocks and figure that out. But figuring out, and I saw lots of you trying to say, well, the top view, some of you did that, right? But those are all things that as a teacher, we can assess our kids on. That child who's doing that has a plan. But when we have something like EQAO, that part doesn't come out. So that's why teachers assess using conversation, observation, and product.
Yes. I'll be honest, I'm not completely sure why they did that. Yeah. I can only think it's something to do maybe to give a clue that this one is the top one of that.
So what we did was we actually used a different color to, because that would be the actual one in the view.
Yeah, we modeled it as a different color. So that way when you're looking at it like that.
Yeah, and again, that ability now, because you want to prove, as mathematicians, we want to prove it for ourselves and build, and we see kids wanting to do that too, that concrete experience.
I was a little bit naughty. I didn't actually give you the 4 responses. See, on your sheet, because I knew if I took those responses away, it'd actually make you think an awful lot more. When I saw this on the eco question, I looked at it and thought, oh, what is it? It's goes there, don't go there. And then I thought, you know what? And I did exactly what I want my students to do. I grabbed some cubes and I built it. And I've been in classes where we've got these sorts of things, and I know there are some students who say, I'm not using those, that's kind of cheating. I say, well, you know what? Call me a cheat, all right? Because you know what? I'm going to build it, and I've just built it just saying, check, left side, front view, top view, good to go. 1, 2, 3, 4, 5, 6. Which one of 3 around? We all get 6? Yeah, we all got 6. Okay. So that was 51%?
52.
52, okay. And last one, which are the following polygons of sides that are all equal in length and no right angles? No right angles, all equal in length. Not square, rectangle. All equal in length. It can't be isosceles trapezoid. It has to be an equilateral, equilateral triangle. How many people got that right?
80%.
80%.
And that's a knowledge question according to EQAO.
So this is something really important. The knowledge questions, those kind of basic questions, we're doing all right in. It's the thinking questions and the application questions that we need to work more on. And as a reminder, in grade 3, we have 12 knowledge questions, 16 application, and 8 thinking. But in grade 6, it changes. We only have 8 knowledge questions, and 16 application and 12 thinking questions. So we're taking away some of the easier questions and replacing them with some of the harder questions. Okay? Right. So one of the things that we'll re-emphasize again and again to become better at spatial reasoning, we're going to go from the concrete to the diagrammatic, and in this case, the symbolic. When we've got a rhombus, you do some work in it, the diagonals, they will always cut each other at right angles. In the past, the way I was taught, copy this definition down, memorize it. I managed to get by because I could memorize some things. I'm a much better mathematician now. I've had some experience with this, and I can apply it in much better situations. Okay? So why did these misconceptions develop? So in getting ready for this presentation, I've drawn some shapes on here, and I want to put some rectangles on, and this menu came up and said rectangles, and I looked at that and I thought, well, no wonder people get confused, okay? Because out of all these choices, only that one's a rectangle. That's kind of got some curves on. That's a blooming pentagon. That's a hexagon. I mean, you can't get much more. There's another hexagon, okay? So this is like really frustrating. This is work, you know, so thanks a lot. Thanks a lot, Bill Gates, okay? And the other thing is that sometimes you get these store-produced posters, which are all done in good intentions. These are two-dimensional shapes. The problem is, if this is all our students see, they think only that can be a triangle. Only that can be a hexagon. And that is where some misconceptions develop, that we have examples which are way too rigid. Okay? And I think
Right. So we're going to do a little bit of talking here about angles. So one of the strands in the elementary curriculum is geometry and spatial sense, and then they have different categories. And we talk about geometric properties. So what do angles measure? Talk in your table. What do angles measure? So we often hear that they measure the distance between two lines. We'll hear those kinds of vernacular. So then when something like that happens, which of these angles is bigger? Right, because now you can see if somebody believes that it's the distance between two lines, it could be, sometimes people think this is actually the bigger angle because it takes up more space on here than this angle. So actually, angles measure turn. So if I start here, thank you, and I turn around that point, that is what I'm measuring. When the child, or when like, and so then this is where you can talk about snowboarding or skateboarding. When somebody does a 360, right, they are measuring how much that person turned. So angles measure turn. It's something that is,
Yes.
yeah.
That's what really much is.
Yes, so this one is a bigger angle in terms of the amount of turn, maybe not, we have,
Question? Go on.
The reference point will determine the angle you're measuring, right?
Okay.
So this will be, if there were two lines coming from the, yeah, so there are two lines going that way.
Uh-huh.
One line from the top, the other at the bottom, and we're measuring the outside angle.
Uh-huh.
So
Okay.
that will explain that.
Right, so now, this is a good thing, is that we didn't indicate which angle, all right? So I could have turned that way, but I could also have turned that way. You see that? And for this one, I could have done that. We did that, didn't we? And this is one of the things that we always tell our students, when you're drawing angles, you have to mark the indicated angle, because each of those you could have two angles there. And this is how misconceptions develop. If we're not precise enough about what an angle is, and many, many adults think angles are something to do with the distance between the two arms. It's a fantastic concept. Angles measure turn, and it extends not just through junior and intermediate, but all the way up into grade 12 when we talk about trigonometry and angles going beyond 360 degrees, and when we're talking about sinusoidal functions and so on and so on.
all right, so we talked a little bit about this one already. We also see when we're talking about different shapes, even orienting them differently. And so I'm kind of keeping a list of sort of some quick points up here. So we have things when it's like a regular shape, it means that all the sides and all the angles are equal. But when we talk about an irregular hexagon, it means that it's still six-sided, but it looks differently than what we traditionally see. So we want students to also see that angles can look different. What I would like you to do, you should have a piece of paper on here. This is known as, well, in our department anyway, I don't know if it's like world known, but I guess we're on YouTube, so it kind of is now, right? Yeah, this is the world's cheapest manipulative. So please find this ripped sheet of paper, whatever color, there's different ones. Doesn't matter. And what I would like you to do is to take your pencil or your pen or whatever it is that you are writing with, and I would like you to put a dot, one that you can see. So for example, anywhere on the paper, does it matter? And we're gonna talk about a concrete experience about creating a tool that kids can use. So, Natalie, do you mind just holding this so that I can talk and fold at the same time? So what you're going to, this is gonna work way better. All right, so what I would like you to do is you are going to fold right through the center of that dot. So no matter where your dot is on your paper, fold right through that center and put a nice crease there. So it doesn't matter, nope, as long as your fold goes through that point. Now this is the tricky verbal explanation, so Natalie will watch and do this. You are actually going to fold the paper again back onto itself so that those two folds go together and still through that point. So wherever your dot is, you are now folding the paper back onto itself. And when you open up your papers, what have you created? You have two lines, so this is good. You have them actually, so there's a number of math concepts that are here. First of all, there is a straight line. You didn't draw it with a pencil or anything, you actually created your straight line. You created another straight line that are horizontal and vertical, so we can talk about that. We can also talk about that they are perpendicular, so when we're talking in intermediate and into high school, we talk about lines being perpendicular to each other. Anyone who's doing construction or things like that, these are great concepts as well. We talk about things bisecting, so it cuts the other line in half. Okay, so we just created perpendicular bisectors. You are teaching grade 7 geometry tomorrow, you're coming with me. Anybody? Perpendicular bisectors happens in grade 7. The other thing that we've created is we've created 4 right angles. Okay, so if Natalie folds that back up for me, you can see where we've created 1 right angle. In grade 3, students need to know whether something is bigger than a right angle or smaller. They don't need to use a protractor, they can use this tool and walk around, go to the park, they can do different things and prove what things in their environment are at a right angle or greater or less. Okay, when we get into grade 3 and grade 4, we talk about things being acute, obtuse, those kinds of things. Now when we open all that back up, we can talk about a straight line being 2 right angles, therefore being 80 degrees.
180.
Did I say that? Sorry. I said 8, wow. I don't know. That's okay. It's because I went to this side of the room. I don't know what happened. I'm not sure. So we have 180 degrees, and when we open it completely, we have 360 degrees. And I believe there is...
Yeah, well, that's a funny number though, isn't it? Can I borrow that for a second, please? So, 360 degrees, half of that, 80 degrees.
180.
Oh my God! What?
Sometimes we finish each other's sentences, sometimes...
Oh, we're not still live, are we? Now we've got 90 degrees. But why is it 360 to begin with? So a complete turn is 360, that's right, but who decided 360? Why is it 360 and not something more convenient like 400 or even 100? That's a good question, I'm glad you asked. Okay, well the people who first thought about dividing a complete turn into smaller parts were the ancient Babylonians. And these are guys like thousands of years ago who realized that the earth traveled the sun and went on an orbit around the sun. And they reasoned it was a circular orbit. And they said, okay, we know from our math that it takes just over 365 days to go a complete orbit around the sun. And so wouldn't it be nice to represent a complete turn as being similar to a complete orbit, okay? But they also were smart enough to realize 365 and a quarter isn't exactly a friendly number, okay? So they said, well, what number could we use that's close to it that is still friendly? Now, they counted a lot in 60s. We count a lot in 10s, they counted a lot in 60s. And 360 was a very nice number for them because it's got so many factors. So they went, well, that's nice enough, isn't it? 360 is good because we can half it, we can quarter it, we can eighth it, we can 10th it, we can 12th it, we can 30th it, we can 60th it, we can do all these sorts of things. Let's decide 360 degrees for a complete turn. And that's why it stuck, okay? 360 degrees for a full turn, 180 degrees, got it right that time, 90 degrees there. I like telling that story is from grade 3 upwards. Because I see it almost as a mnemonic, almost like as a memory device, why it is 360 and not some sort of random number like 400 or 120 or whatever it is. Okay, so if your sons and daughters are ever asking you about this, share that story with them. Okay?
So imagine reading the definition of a turn, and what Mike had said in a textbook is different when you experience it. So we're gonna go and look at this particular diagram. And we're gonna try now and figure out, yeah, you don't have yours. It's all up here. So we're gonna try and figure out, can you imagine which of these nets, so a net is a flat skeleton of a shape, can you imagine which of those actually fold together to create a cube? And I see some gestures, and then I see some people also going like this.
You can tell we're in a Catholic system. Oh, I know the crosswords. Yeah, that's always, and when they do it, that's always the first thing they do. I'm going to confess, this is the sort of work I was presented when I was going through school, and I found this very difficult. I got some right, I got some wrong. There's more by luck than judgment. When I first started teaching this, so in grade 4s and grade 5, and I came across these things, it completely changed the way I do things. And now I can do things which I couldn't do like 20 years ago, and I'm a better mathematician as a result. Does that fall together to make a cube? Okay, fits and giggles. Hands up if you say yes. Hands up if you say no. He gets voted off the island. Okay? So let's have a look. Let's prove or disprove.
Math buffs.
Math buffs.
So we don't have these manipulatives at home, right? We have them in our schools. So something at home that you might do is look at a cereal box. Get them to cut it apart. When they're doing rectangular prisms, there's lots of work that we do in those junior grades to talk about what they look like.
What's the Pillsbury dough thing?
Yes.
The one pops open. So you got a cylinder, and that pops open. Can you picture what shape that comes? You've got the two circles, top and bottom. But what about the label bits? It's actually a parallelogram. Oh, think about a
Toblerone bar. Can we
I was
talk
gonna
about the
say-
Toblerone bar?
I was going to say toilet roll.
Oh, okay, we'll go with toilet roll, but I was going to the Toblerone bar.
Okay.
Because let's talk about the triangular prism.
Okay, yes.
Right.
So here we go. What about this one? Will that fold?
Yes.
Hands up if you say yeah. Hands up if you say no.
No.
Prove it for me.
But even all of that and all the thinking that happened, I love it. Because once you got it in your hand, then you can envision it. So we're going to show you some experiences that kids are having with these in schools.
This is a grade 5 class at St. Mark's. Okay? And I just said, find as many rectangular, as many nets as you can. Okay, that one works, beautiful. How about this one? No, that one doesn't. This is my favorite one. Yeah, it's gorgeous. This one, I didn't discover myself. When I first did this, I didn't even realize it worked. And another kid discovered it, okay? So in the space of 20 minutes, they came up with all 11 nets for the cube. And we had such fantastic discussions, like, is that the same as that one? Some kids thought yes. Is that the same as that one? Some kids thought yes. Some kids thought no. That was all right. We had a good discussion about congruence. that a shape can be reflected or rotated, a mathematician would say they are still the same. All right? So it's one of my favorite things to teach, and the experience they had was absolutely fantastic.
And you could, I don't know if you saw in the background, then they were writing down the ones. There was paper that they had to draw. So we want them to have that concrete experience, but then we want them to also to consolidate it in that diagram so that they would move, because eventually you can't carry those around in your
No.
pocket, right? Like that's just impractical.
Well,
So we can't, right? All right, so you also have something in, I was gonna say on your desks, but bear with me. These are called geoboards. And if you have a smartphone, there is a geoboard app. So if you go to the App Store and put in geoboard, you will get an app that has this diagram. So,
That's on the front cover of the-
yes, and okay, and on the front cover of your handout is the geoboard app as well. So they give you a bunch of elastics and you can kind of do this virtually. Kids like to actually even just play. So you have elastics and you have a geoboard. And yeah, lots of kids just like to kind of experiment a little.
Actually, this screenshot here, my daughter was playing on the iPad one day when I was driving there, and she's on there, and I just said, make me some trapezoids. And she made me some. I said, make me a trapezoid that's got a right angle. And she did that. So I was just calling things out in the car, and that's what she did. She took a screenshot.
All right, so I am going to do my super math trick right here. Actually, well, it's just like a life trick. It's mind reading. I want you to make a parallelogram on your geoboard. And you're allowed to talk,
Yeah.
right? Because this isn't like a test or anything like that. So what is a parallelogram? You have somebody beside you that maybe can.
Oh, I gotta lengthen it all there because I can't. Okay, you did that way. Oh, see, some of mine are missing. I
Wait,
don't
you
go
got it?
another way.
When you've got your parallelogram, hold
Okay,
it up.
so, wait.
Take a look around. You can show other people. Yep, we've got the app already in use at the back. Excellent. Yeah.
Nice seeing you guys. Nice seeing you.
I don't know.
All right, so lots of you have, this is where I feel that I can, well, can you just hold yours up and we'll take a quick look around? Most of you have one that looks like this. Okay, most of you have a parallelogram that slants to the right. I know, because our experience has been that, and that's okay. If you rotate that, you still have a parallelogram. But it looks different and it's not what we normally go to. So that's why we want kids to see parallelograms can look like this. So I'm gonna borrow yours. It can also look like that. That's still a parallelogram. And it's in fact your same parallelogram, we just rotated it. These are all parallelograms.
That's meant to be a square. But again, it's kind of distorted. So
Yeah. But yeah, some of you went to the rectangle first. But most people, when they hear parallelogram, they went to that initial one. But yes, a rectangle is a parallelogram. A square is a parallelogram. So those are some conceptions or some concepts we want kids to know as well.
So in this idea of the properties of what is it that makes a parallelogram? And sometimes we'll say these are all parallelograms and put a bunch of shapes up like this, and we'll say these other shapes, they're not parallelograms. And we get the kids to think, well, what's it saying about this group that's different from all the others? Again, I was in a grade 6 class and I did that, and they were able to see that all of these have got something in common. Firstly, you've got 4 sides, okay? And then secondly, they were able to tell me, in their own words, this side is parallel, and this side is parallel. So then you paraphrase, so you're saying that it's got two pairs of parallel sides out opposite each other. So four sides and the opposite sides are parallel, yeah? Okay, so that's okay, a square's good, a rhombus is good, we're good to go. That is what a parallelogram is. But it's so helpful when they try and make it themselves first. Again, where I learned it, just copy a definition there.
All right, so can you make a triangle with 3 different side lengths? And it's great seeing people proving it to themselves and to others. If you make a mistake on something like a GeoBoard app or here, you can easily fix it. When we make a mistake with a pencil and paper, kids have to erase it and they get frustrated here, just change it, right? Talk to your partner, prove it. Here's another one. Can you make a triangle with an obtuse angle? So obtuse makes, and you're welcome to use your...
Use your 90 degree to check to see if it is bigger than 90 degrees.
So obtuse is larger than a 90 degree.
Yeah, beautiful. Yeah. Oops. That's a very cool. Yeah.
Can you make a triangle with 2 obtuse angles? 2 obtuse angles. Yeah. Why? You got it, yes. Okay, so the angles have to be within the triangle. But no, you can't have a triangle that has 2 obtuse angles. And I like some of you tried to picture that in your head. That's that symbolic thinking, and then you proved it with your talking, and you proved it with your geoboards, right? So there's lots of different parts. We're talking triangles into grade 7. We're gonna kind of move along just to the last one on here, because it gets back at this one point. Can you make a hexagon with 5 right angles? So a hexagon has 6 sides. Also, you're trying to...
Cool. I'm pretty sure she got it.
So try it. 5 right angles.
Yes.
Oh, sorry. Should have brought that over to you. Well, you have 2, so I would keep it. You have 2 right angles. Can you imagine trying to do this on graph paper and how frustrating, right? At least here, that's great. And we could, so in the order of the evening, I'm gonna tell you it is possible. But we do have to move on. But you are welcome to try it on the, I will prove it at the end, but we do have other things, because we want to talk about other things where spatial reasoning applies in other strands beyond geometry.
So what we're going to do in the next 10-15 minutes is move and show how really a circle is just a rectangle. Okay? Well, yeah, with a bit of adjusting. We're going to talk about something that's near and dear to my heart, that's developing formulas. Okay? As we develop these formulas, kids, we've got a winner. Or in this case, the hexagon. Yeah. So I want kids to understand what the formula for each of these shapes are, and then they're in a much better position to memorize it and apply it. I think we're all pretty comfortable understanding the area of a rectangle. And when I developed this with grade 4s and grade 5s, we connected to something that we already know. And if I can connect something that is some new knowledge to something that is already known, it is going to last much more. So in younger grades, they do a lot of work on arrays because that's a fantastic way to learn about multiplication. So this is basically an array. It is 5 going up and 4, 5, 6, 7 going across. And a simple question you'd ask to a kid in grade 3 or grade 4, how many squares, they're supposed to be squares, how many squares are there? And some kids will do it in different ways. Some will count by ones. Some might see, oh look, there's 5, 10, 15, 20, 25, 30, 35. Some might see the 7s and say, you know what, I fancy counting in 7s because why not? 7, 14, 21, 28, 35. And that's great, but then there'll be a point where they'll say, oh, it is just 5 times 7, or 7 times 5. Absolutely. Now, what if I didn't tell you this number, and I didn't tell you this number? What would you do to work out the area? And what I'm getting at there is that they say, you just take those two numbers and you multiply them together. All right? So we got that. So now we can say the area is equal to the length times the width. And everything we're going to do now is going to be connected to the rectangle. You all have a small rectangle. It should be kind like 50 edges there. Can you just choose one of those now, please? There's enough for one each. And I want you to write down the area of the rectangle that you've got. Okay? Have you all written it down inside yet? Other than rectangle. Oh. Yeah. Not there. I'm only joking. Now what I want you to do is somewhere on the top edge, I just want you to put a dot anywhere. Actually on the edge though. You see what I've done there? Anywhere on that top side. And then, using the rulers that you've all bought, I want you to join this to the bottom right angle there, like so. When you've done that, take your scissors, and you only get one chance of this. So you're basically going to cut along that line, as I'm doing here, to create two pieces, a bit like you can see there. Okay? Pass the scissors carefully. Now you've got two pieces. What I want you to do is rearrange those two pieces to make a parallelogram. And I promise you, it is possible for every single one that you've done. And if you're puzzled how to do this, just take this triangle, you can shift it along, put it there, parallelogram. Okay? You all right with that? Happy? We've all got a parallelogram. Anyone knows a parallelogram? Four sides, opposite sides, parallel and equal on length. Thank you, fantastic. Now work out the area of that parallelogram. Yeah, when I do this with the kids, they go, oh, we've got to count all the squares. Do we have to count the half squares? What about this one? Until someone kind of says, hang on, it's just the same. And I said, well, what do you mean it's the same? Well, look, you take this bit. It's just the same as a rectangle. You didn't like cut anything else off. You didn't like make bits disappear. It's still the same area. So we don't need to worry about all these half or third squares. It's the same area. Right, fantastic. Now look at your parallelogram. Can you see the important measurements that you would use to get the area without cutting it back into a rectangle? Well, I tried to highlight them beforehand, but can you see this, the base? And then this one, the height. So these two measurements, really important. They are perpendicular to each other. They cut at right angles. A common misconception that kids do really comes up on grade 6 EQAO. EQAO will give this one, and this one, and they'll multiply these two. They think it's kind of like a rectangle. It's the perpendicular one. So I find that when I do with this, kids are far more likely to look for these two perpendiculars. So from here, we can say that the area is equal to base times height. Okay? Did you learn that in school? Area of a parallelogram is base times height. Probably.
Probably, but sure.
I'm pretty sure we did. Did you understand it? Is it something that you might have forgotten or mixed up with something else later on? This is really important. One of my favorite words in the curriculum is develop. We don't say give the formula, we say develop. And something like that is a 20-minute activity for me as a teacher. Okay?
Now, Mr. Jacobs, we talked about the other D word. Does it say discover the formula in
Discover the formula? Well, the kids think they discovered it. I mean, they think they're Pythagoras, when they discover it, So whoever actually says, oh, it's base times height, all right, yeah, Anne's discovered it. Anne's rule for the area of a parallelogram is base times height. But as a teacher, I'm guiding that discovery.
So it's called develop, and you will hear discovery math. So they're in our Ontario curriculum. You can look up the Ontario curriculum. It's a public document. You can put in the search and say discovery. Discovery doesn't actually happen in our curriculum. We talk about develop the formula. So it's a little misconception that is important.
So, you've all got a parallelogram. If I draw any diagonal, I've decomposed it. What shapes do you see? Two triangles. Okay, let's have a look at the first triangle. What can you say about that shape compared to the other triangle? They're the same, all right? Let's see. I saw your little hand gesture there. They are the same. We know that the area of a parallelogram is base times by height. So what do we know about the area of a triangle? Base times height divided by 2, or half times base times height. Okay, this now is the way I develop it. I start with rectangles, then parallelograms, then triangles. When I first started teaching, I did rectangles, triangles, and then this. It's a much better way this way. Okay? Next one. Oh, right. Oh, go. That's good. Okay? I just got a bit carried away with stop motion and animation, and I made a vine. All right? It goes a bit quick, so I'm going to show you this way. Okay? Here's my trapezoid. Four-sided shape with at least one pair of parallel sides. I'm going to get a second copy. So here's my first copy. Here's my second copy. And I'm going to rotate it and put it there. What shape do I have? Parallelogram. Area of a parallelogram is base times height. Yeah? This parallelogram, if I call this top measurement A and this bottom parallel side B, what's the complete length from ear to ear? A plus B. So the base is A plus B, and the height, well, I can just put that down there like that, the height times by H. Oh, but I don't want that, do I? Because that's a complete parallelogram. I just want that. So what do I do to get the trapezoid? Divided by 2, or half times height times A plus B. So for years, I just plugged the numbers into the formula and didn't realize why it's A plus B. Now you're thinking, oh, is that it? Okay? So we developed the formula. We did this upstairs, second floor, with a grade 7 class just 2 weeks ago. And we got them to tell us in this manner that the area of a trapezoid is half times the height times A plus B. Right, I did promise you that I'd show how a circle is really just a rectangle. There's lots of online things we can do, but I think I'm just going to do it this way. Now, one of the things we need to know first is that the circumference of a circle, you might have remembered, is 2 times pi times r. Okay? And you need to know this for this. And I'm going to do this. I'm going to just decompose it. And when I decompose it, I want you to tell me what sort of shape you see. What sort of shape do you think it's about? It's about a parallelogram. Now we want the base. Okay. Do you see the base there? Do you see it's part of the original one? Circumference. So I've got some of the circumference there, and I've got some of the circumference on top. What was the circumference of a circle? 2 pi r? Okay, so I'm going to say, have I got pi r on the bottom and pi r on the top? We okay with that? So approximately, this is about pi r. Okay, and what about the height? I'm going to draw it here. What the heck, That's the height, isn't it?
Yeah.
Well, it's the radius. Absolutely. Yes, you're getting really angry with me now.
It's okay, it's for math.
Area of a parallelogram is base times height. The base is pi r. The height is r. Pi r times r, a little bit of algebra, and r times an r is the same as r squared. So the area of a circle is pi times r squared. And if that doesn't
Mic drop.
if that doesn't touch your crumpet, I don't know what. Okay.
And so this is grade 8 measurement. So that spatial sense that we've been developing all along, but this goes all the way into high school then, where they learn about the volume and surface area of cones and spheres and those kinds of things. All of those are happening.
So decomposing shapes, as you can see, taking a circle and split into small sections and rearranging. It's a really, really, really powerful tool. And so we've got one or two things I want to share with you. This was our problem of the week on our Twitter feed a few weeks ago. It's on the very first page of your handout. And one of the things I like about this is that the answer isn't immediately obvious. There's sometimes in math there, I think we give questions where you're going to give me the answer pretty much straight away. What's 20 plus 30? 50. What's half of 360? 80. 180, sorry. Okay? That sort of thing. Okay, but there's other times you gotta work a bit harder for it. And this one here, decomposing shapes, I think it says split this rectangle into 7 smaller squares. The side of each square must be a whole number. I'm just going to give you a couple minutes just to play with that. So I'm looking for squares here. One of the things I like about doing these tweets is every now and again, classes will tweet me their solutions. Sometimes parents as well. And people from all over the world sometimes tweet me their solutions. Can they overlap? Very good question. No, they can't. It is. That as you're doing this, one of the things I'm just going to encourage you that I've learned to do, remember earlier on we said spatial reasoning is malleable. We can get better. But we've got to try some activities to get better. So it's okay to try this and not get the answer straight away. Erase your work, try again, keep trying. This is one of the things I've learned over the past few years, and it's really helping. So, if you don't want to know the answer, close your eyes now. If you want a hint, keep them open for about 10 seconds. Okay? So, 1.
No? Because we have faith in you. We have extra copies if you want to take it home and puzzle through it.
Okay. They want to see it again. If you don't want to see the answer, close your eyes. So, one of the things, if you're looking for things to do at home with the kids, I will say, if you follow us on Twitter, every week we put out a problem of the week. Try it with your sons and daughters. I try and aim this to kind of like an upper primary and above age in terms of the math content. But yeah, try it. Funny story about this one. This is a question I saw. And again, it's maybe a bit of weakness on my part. I looked at that. This is on the front thing there. Some of you might have tried this one. And it's a lesson I think is worth repeating because I looked at that and I thought, oh, right, no, oh, right, gosh. Pythagoras is going to come in here. Nothing obvious is sticking in here. You know what I'm going to do? I'm going to algebra the heck out of this problem, okay? And that's what I did, all right? And I came up with an answer, a squared, the size of the square is equal to 8. Passed myself on the back, and I'm thinking, yeah, you know what? I think I just took a sledgehammer to open a walnut there. There's 8. That's not quite a nice number, isn't it? It's not like 8 and 4 ninths, something like that. 8. There must be a better way of doing that. And I thought about it, and I came across a better way. But I also the next day went in the office and I said, Christine, have a look at this problem. What do you think? Christine said, how about we decompose it?
Sorry.
Do you see what we've done here? And this is something which I'd forgotten, I've been getting better at, is that sometimes, don't jump into the algebra. Sometimes, just draw some lines in there and see where it goes. There's no handbook to solve this problem. Just try some of it and see where it goes. Play around with it.
So this is significant here. And then how many of those triangles fit within this triangle? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9.
Area of the whole triangle is an isosceles one. 6 times 6, 36. Half of that, 18. There's 9 of these triangles. 9 of these make 18. What's one of them going to be? 2.
And then 2, 4, 6, and 8. So by recomposing that initial shape here, then I could figure out, so yeah, base times height, got the 36, divided it by 2, got 18, and then figured I can fit 9 of those congruent triangles in there.
Now, there's nothing wrong with what I did. I still think it's very pretty and poetic in many ways. Well, maybe. Okay, beauty's in the eye of the beholder. And there's be time and place for that. It'll be more powerful sometimes to use an algebraic approach. But can you see that sometimes, if you've got good spatial reasoning, it is a much better tool to attack the problems. If all I give my students is algebra, 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 it's not going to make them as an efficient problem solver if I do spatial reasoning combined with nonsense. Right, now we get to the fun stuff. Well, it's all been fun so far. Now we get to the really fun stuff, okay? Again, just for fits and giggles, you're not being tested on this. I'm not going to take your papers in. I want you to sketch a picture that shows me what the Pythagorean rule is all about. And if you want to abstain, I'll allow that, okay? Sketch a rule that tells me what the Pythagorean rule is all about.
Now, if I ask my dad fully admits that he does not know the Pythagorean rule, but he knows this 3, 4, 5 rule. So if any of you are in carpentry or are in some of the trades, you might know a rule that's called the 3, 4, 5 rule. It is also related to the Pythagorean rule.
I'm just taking a wander around to see where we're at.
Yes?
Okay? Now, I do this with adults a lot, and the common response is, I'm not even sure I remember the Pythagorean rule. I think there's a triangle involved. I think it's a right-angled triangle, and I get a sense a lot of you might have remembered that. There might be some square, a squared or something. I'm not quite sure, you know? And
We
to
asked
draw it-
Siri. That's the other question.
Can we ask Siri?
Yes. If you ask her for the Pythagorean theorem or something like that, no, yeah.
See, so yes. Okay. Okay, so if you turn to the... Okay, so some people say a squared plus b squared equals c squared. And yes, that is right. But that doesn't answer this question.
Yes.
So, and this is one of the things I've taught students, you know, in the past 30 years, oh yeah, a squared plus b squared equals c squared. I said, yes, but what does that mean? And they're not quite sure. And that's kind of dangerous, because that knowledge will only take them so far. And really, the way the curriculum is written, it develops a formula in a beautiful way. And on the back of your sheet, this is a diagram that demonstrates the Pythagorean rule. Can you see the right-angled triangle in the middle? Yeah? And for whatever reasons, I've drawn a square on each of those 3 sides. The 2 shorter sides and the longest side. Okay? Who discovered the Pythagorean rule? It wasn't Pythagoras. No, it was actually discovered by, I think the Chinese discovered it 1,000 years before him. And I think there's some Indian mathematicians as well. This Pythagoras got all the credit. Yeah, he's like the glory hockey player, does a little tap in at the end and gets all the credit for it, all right? What I want you to do is let's discover the Pythagorean rule the way it was discovered, and that is geometrically, okay? You've got some cubes on your desk, okay? And perhaps you can work as a table here. What I want you to do, can you see the smaller square? Can you find out how many cubes you need to cover that smaller square? In other words, you're going to tell me, okay? And when you do that, actually place it on the square. Just a smaller square for the time being. Just a smaller square. Okay, so this is here. How many do you need? I see this. Okay. Yeah. I got it. Okay, good. Right. Now, I want you to do the same thing for the middle-sized square.
So keep the smaller square.
Keep the smaller square there, please. I think you got 9 on that smaller square, yeah? You got 9 for that smaller square? Now, use the other cubes that you've got and get the area of that middle square. Yeah, you got it. Yeah. How many do you need for that second square? 16. So we got 9 for the smallest square, 16 for the next one. And I think a lot of you are one step ahead of me. Take those 2 squares, rearrange them, and put them in the large square. I'm just getting a glance around to see where we're all there. And when we do this with students, it is pretty neat seeing the light bulbs go on. Oh look, those 2 smaller ones, you take them apart and put them together, they make the larger one. I say, yeah, so what's 9 and 16 make 25? Absolutely. That is what the Pythagorean rule is all about. It's not just about triangles. It's about the area of the squares on there. So that is our concrete introduction to it. How do you apply it in life? In lots of different ways. Actually, one of the ways I hadn't thought about before, it's used in construction in all sorts of things, in framing and whatever. But one of the ways that was, a parent once explained to me how he used it. He said he's one of these people who goes in and does the surround systems for home theatres, yeah? And he says his life is all about the Pythagorean rule because the distance from the speaker to where a chair is a diagonal distance, and you've got a horizontal bit and a vertical bit. So if he knows that bit and he knows that bit, he can work out this distance. And this distance is very important in making sure he puts the speakers in exactly the right place. It's pretty cool, yeah.
And so my dad, who doesn't know the Pythagorean rule, he installs carpet and tile. If you didn't have your tile square in the room, you would know that. So he knew to measure 3 out on one wall, 4 out on another, and then that needed to be 5, so that you can tell if the walls in your house are square, and if not, then you need to compensate. So there's the application part to this. The 3, 4, 5 rule, you just learned it because 3 squared plus 4 squared equals 5 squared.
Now, Strictly speaking, that's not a proof. We just prove it works for one triangle. Okay? Does it work for all triangles? Well, with other examples, we get kids to see that, yeah, if you draw a square here, this one and that one, you tell me what's going on. They'll say, oh, like a squared plus b squared equals c squared. Yeah, that's right. A squared plus b squared equals c squared in a right angled triangle. And the kid who tells me first say, can that rule be named after me? I say, no, you can't. It's always going to be the Pythagorean rule. Okay? Perhaps the most beautiful demonstration of this is this one here. I don't know if you've seen this. A squared plus b squared equals c squared. And c squared is equal to a squared plus b squared. I was in a grade 9 applied class 3 weeks ago. We're doing some work on the Pythagoras, and when we showed this again, the light bulbs just came on. Oh, that's what it's about. And when they see that, they're less likely to make the mistakes when they substitute the numbers into the formula. They're more likely to put the right numbers in the right places and know when to add and know when to subtract. Okay? Concrete, diagrammatic, symbolic. That is how we develop the understanding of the Pythagorean rule, of all the formulas that we talked about, from rectangles all the way up to circles and beyond. Okay, this is how we develop it. Anyone who says that this is discovering math and it's bad is completely misinformed. All right, I've got loads of experience about this. I've taught it one way, memorize this formula, and after a week or so, the kids forget the formula, or they confuse it with something else. This way, it lasts much longer and the kids understand it.
Sorry, my
yes.
brain is hurting a little bit.
Okay. Wait.
Just a question, if you, so not in a diagram, what would have been the thing that I would have learned? Like, what is the Pythagorean theorem for? Is it the length of the line of the
Fantastic
triangle?
question. So once we will get to a point where we'll say, kids, do you need to draw the rectangle, do you need to draw the squares anymore? And say, you know what? I can picture where they are. And so it will be something like this. And we'll say, okay, so let's look at this one. This is 5 meters. This is 13 meters. We need to find this one.
That's how.
Okay? Now we become diagrammatic, a little bit symbolic. I can picture a square here. Okay? 5 squared. I can picture a square here. I'm just going to call it x squared. And I know this is going to be the largest one. Okay? A common mistake before I started teaching this way is that they always put the 5 and 13 together. When I do it this way, they know it's the 2 smaller sides. So go there. So what's the area of that? 25. What's the area of that? I don't know. What's the area of that? 169. Okay? I need to find this one. What am I going to do? When I teach you this way, oh, I've got to do the larger one, take away the smaller one. Okay, x squared is equal to 169, take away 25. Okay, x squared is equal to 144. That's the area of the square. I need just the side. I need to do the square root of that, which is 144. And from there, x is equal to 12 or negative 12, but we're not going to have negative numbers. Okay? And that's what it is. And again, I'll be right up front with you. When I first started teaching, I just went straight to that. I went straight to the symbolic. I went straight to memorize this. Memorize the formula. Some kids got it, most didn't. And the kids who got it, they got it for 2 or 3 months. When they went back to it, not all of them got it. Doing it this way, developing it, discovering it the way it was discovered concretely by the predecessors of Pythagoras is why it's written like that in your curriculum.
Yeah. I don't know. Yeah. And to tie it back in, and it's not always about EQAO, but it's such a public way for us to think about math. they're given in grade 9, they're given the formula sheets. There are ones that are produced by BQAO, they are given the formula sheets. They are given a squared plus b squared equals c squared. Because that's a knowledge and memorization part. And then they're given a thinking and application question. And if they have trouble with any of those things that Mike said, like putting it in the wrong place, that's what's going to happen. So they don't have to have this memorized.
We're kind of running out of time. What time are we finishing? 11 o'clock?
That's what the bouncer said.
That's it. Okay, so very, very quickly, one of the things I want to share with you is, again, something that's near and dear to us, is this idea of transforming things. So there's 3 basic transformations we'll learn in primary, junior, and intermediate: reflection, rotation, and translations, or shifting shape. This is an EQL question. It is on your sheet, okay? And I think 60% of our students got level 3 or above. They reached provincial standard. Provincially, it was 50%. So our board was outperforming the province at this, okay? Why are we outperforming the province? Because we've done lots of work with our teachers when we go in to where we're teaching, say the best way to learn about transformations is not to try and picture it in your head, because a lot of kids, a lot of adults struggle with that. The best way is to use something like this, a bit of tracing paper, or what's the other word you call this?
Tissue paper.
Tissue paper, thank you, yeah. This is actually parchment paper. I stole from my wife, okay? Don't tell her. Oh, the lie stuff. Oh. Thanks, Jackie. Okay, and one of the ways we work with this, I'm going to see if I can do it, is not quite big enough. You're going to have to do it on here. You actually trace the shape. Oh. You trace the original shape and say, what do I have to do to go from shape 1 to shape 2? We just flip it. Another word for flip is a reflection. Okay? Now, when we reflect it, we can just say, oh, we reflected it, but we can be a little bit more precise because we reflect it in a line of reflection. So your question says, name of transformation, a reflection, but they will accept flip. Okay? And then says the description. And what we're looking for there is for our students to actually draw the line of reflection on there. Okay? So we're here now, we're at shape 2. Shape 3. What do you do to go from shape 2 to shape 3? From shape 2 to shape 3. I love the gestures, okay? You rotate it. Now, some kids find it difficult, but you give them tracing paper and they rotate it. Yeah, we rotate it. Now, with the rotation, how do we describe it? Well, where would you put your pencil on to actually turn it? I think it's that bottom right-hand corner, is that right? And how much do you rotate it? Which way? Yeah, clockwise. I have to think about that. Yeah. So here it would be rotate 90 degrees clockwise. Okay? And the last one, once you look there, you go from here to here, you're shifting over, aren't you? How much are you shifting over? 1 step, 2 steps, 2 steps, which direction? 2 steps to the right. Okay? So that's what we're looking for to meet provincial standards there. All right? And again, it's just a simple little thing to use tracing paper to show that. So if your son's adult has come home and said, I've got some homework and it's about, I've got to reflect shapes or rotate them, I'm not quite sure what to do, grab some parchment paper or some tissue paper and take it from there. Okay? And So we're going to end with this. This fella, Donald Coxeter, was the world's best geometer. He died a few years ago. Originally from England, but he did the vast majority of his work down the road at the University of Toronto. And his geometry that he did was not just two-dimensional or three-dimensional, it was multi-dimensional. Okay, he could see cubes in 4, 5, 6, 7 dimensions. And his work is so far-reaching, is that they use his work to, you know when you go on Amazon and you buy a book, and it says, oh, people who bought this book also bought this book. It's actually based on his geometry, because it's taken all your information, all the bits about you, what you bought, how frequently you buy, your age, your eye color, length of hair, I don't know, keep that, but they take all that and they do some sort of transformation and match it with similar people. But this is something that's done in multi-dimensions, okay? It's not just a simple two-dimensional reflection or rotation. It's multi-dimensional. It is all based on his work. This is him in action. You just click the next picture. Look what tools are he using to understand about symmetry. So the world's greatest geometer is using mirrors and tracing paper and physical objects to understand about symmetry. What do you think our students need? They need that as well. So any curriculum must have some things. This is his quote. Best path to learning is hands-on, leading to the thrilling intellectual buzz of a self-made discovery. So when kids say to me, oh my gosh, those two small squares, they make the largest squares. That's fantastic. Guess what? You discovered Pythagorean rule. Oh, pi r times r, I saw it today when you did that. It's pi times r squared. Well, that makes sense now. Where was this 30 years ago when I was at school? Sorry, 10, 20 years ago. Okay? Yeah, okay, great. Yeah. So, what can you do? Okay, in the youngest age, any sort of jigsaw puzzles, fantastic. Playing with blocks, fantastic. Playing with Lego, fantastic, as long as they pick the bits off the floor. Okay? Games, fantastic. Blockers is a brilliant game. You see your sons and daughters, they're rotating and fitting there. They're doing rotations, reflections, translations. Okay? Canoodle is another wonderful game, great for a car journey. It's trying to fit pieces into an outline, and you've got a booklet of, you might be given this one, and this one in the right place, and you've got to find out where the other four go. Keeps my kids quiet for hours, I won't say hours, maybe 10 minutes. Yeah.
So just to repeat that, there is a Canoodle Junior. Keep your 4-year-old. Yeah.
There's another game called Tantrix where you've got to like put tiles together to make sure you've got one continuous loop of the same color. Flow Free is a fantastic app. It's a free app where they've got to connect the dots of the same color together. And again, that is one is, you know, if my son or daughter say, can I borrow your iPad just to play this app, say, knock yourself out. It's good for you. Okay. Pentago is another great game. It's a bit like Nuts, a bit like tic-tac-toe. Okay, you've got to get 5 in a row, but each time you put a piece down, you can rotate one of those. I need to play this more because I need to get better at rotations. Okay, that's one of my weaknesses still. My kids still beat me at it. Okay.
Tetris is another.
Oh, Tetris, of course, yeah. An oldie but a goodie. Yeah. So that is the joys of spatial reasoning. We could talk till 11 o'clock, but we've all got talks to go to. Thank you so much for coming. Thank you to BC for hosting us and for the refreshments and everything. Feel free to what?
Take cookies home with you.
Take cookies home with you.
And please join us on May 14th. We will be doing problem solving, and of course we'll be doing it much the way we've done our other math cafes, talking, you doing math, you having some great things to take home. There are a few pointers over here if any of you want to take a photo of that before you go. If you want a blank copy of the papers, we do have extra. Feel free to take some home with you.
We've got lots of extra. Don't forget, look out for our comms of the week. They come out usually every Monday. At DCDSP. Alright? Thanks very much for your attendance, guys. Have a safe trip.
Take care. Stay safe.
Great job. I'll look at